Today, we're happy to resume our Zoominar with Michael Hutchings, who tells us about rebel with frequently intersecting a symplectic surface.
All right. Thank you very much for the invitation. So this setup, this is just some basic definitions. Probably everybody knows, but we have a Y is a closed connected three-manifold. Lambda is a contact form on Y. We define the contact volume to be the integral of lambda wedge d lambda with respect to the orientation determined by lambda wedge d lambda. So that's some positive number. We have the contact structure Xi, which is the kernel of lambda. We have the associated Reeb vector field, which is in the kernel of d lambda, and it's normalized so that lambda of the Reeb vector field equals 1. And we're interested in periodic orbits of the Reeb vector field. So these are maps such that the derivative of gamma is the Reeb vector field of gamma of t. And the period capital T, we also call the symplectic action of the periodic orbit. So the general kind of question we want to ask is, do these exist? What can we say about them? Can we say anything about their symplectic actions, or maybe some topological properties? What can we do? Now there are many results about this question, and I can't give a comprehensive history. So let me just briefly mention a couple of things which are related to what I'm talking about. So one milestone was in 2006, Cliff Tobbs proved the three-dimensional case of the Weinstein conjecture, which says that for any closed three-manifold, there's at least one Reeb orbit. There were various, was known in some cases by Hofer and other people. Now, in many cases, there are actually infinitely many orbits. So, and in most cases, it's known that there are either two or infinitely many Reeb orbits that are different in the sense that their images in Y are different. So this is known in the case when the contact form is non-degenerate by Kalem, Darnois, and Reshman. And that non-degenerate means that the Reeb orbits are cut out transversely in a suitable sense. And it's also known if the first Chern class of the context structure, which is some two-dimensional cohomology class, is torsion, by Dan Christopher Gardner, Bertrand, myself, and Wei Liu. So this holds, for example, for any rational homology sphere. The remaining open case is where both lambda is degenerate and the first Chern class is not torsion. And Irie proved that generically, not only are there infinitely many Reeb orbits, but they're actually dense in Y. So every point in Y, any small neighborhood has some Reeb orbit going through it. And he further showed that generically, the Reeb orbits have a certain equidistribution property. I'll say later what it says exactly. Oops, what happened? So there we go. So what I want to talk about today is some existence results which don't require any kind of genericity. So there's some Reeb orbits with certain properties which are guaranteed to exist no matter what. And the setup is I have a surface in my three-manifold, which I called admissible symplectic surface. So it's almost an embedded surface. So it's embedded except on the boundary, or one way to say it is that it's a map from a compact oriented surface with boundary into Y, and the map is an embedding on the interior sigma. On the boundary sigma, all I know is that it's an immersion. And the image of the interior is not allowed to intersect any of the boundary. And furthermore, the Reeb vector field is positively transverse to the interior of the surface, and equivalently, that means that D if the contact form restricted to the interior of the surface is a symplectic form on the surface. And the boundary of the surface, on the other hand, is parallel to the Reeb vector field. So I assume that for every boundary component of sigma, its image under this map U is the image of some Reeb orbit. So that it could sort of cover some Reeb orbit multiple times, but it's a Reeb orbit. And I define the area of the surface just to be the integral of d lambda over the surface, so that's some positive number. Now, there are lots of examples of these. So, for example, a theorem by Colan, Dernwa, Reeb, Ritz, and Rechman said that generically the contact form admits a Birkhoff section, and that's an admissible symplectic surface, as on the previous page, with an additional condition, namely that if you start at any point in y and follow the Reeb flow, either in forward or backward time, then you're going to eventually hit the surface. So my admissible surface, symplectic surface, it doesn't assume that. So like if you take the surface and you flow it in infinite forward and backward time, you might not necessarily cover all of y. Anyway, so generically these Birkhoff sections exist. So, and those are examples of admissible symplectic surfaces. Another way that they arise is if you have if the contact form is non-degenerate, then there's a UMAP, an embedded contact homology, which is a certain count of index 2 holomorphic curves. And this is known to always be very non-trivial on the homology. So there have to exist a bunch of holomorphic curves which generate the UMAP, or which the UMAP is counting. And for such a curve, if you're lucky, so the holomorphic curve lives in R cross Y, but if you're lucky, if you project it to Y, you might get a curve, you might get an embedded surface, except for the ends of the holomorphic curve are asymptotic to Reeb orbits. And so then that will give you another example of an admissible symplectic surface. Okay. Now, before stating my theorem, I have to introduce an additional technical hypothesis. So suppose I've got an admissible symplectic surface. I say that the contact manifold in the surface, all this data is nice if for every Reeb orbit, which is in the boundary of the surface, there's some neighborhood where the Reeb flow looks like a rotation. So the neighborhood is identified with a circle across a disk, and the Reeb flow. So it goes around. This d by dt is the circle direction, and d by d theta is the angular polar coordinate on the disk. So it's saying that I'm rotating in the time direction around the circle, and I'm rotating in the theta direction on the disk, and the radial coordinate on the disk is never changing. So the return map is actually rotation. This is a non-generic condition. In particular, it implies that the Reeb orbit is elliptic. So ideally, if I were smarter, I could drop this hypothesis in my theorem. So I need a little meme for this. So if I had the big glowing brain, I could drop the hypothesis, but I just have this little dark brain. Okay. So here's the statement of the theorem, and it's in this archive preprint if you want to see more details. So let Y be a closed three-manifold, lambda be a contact form, let U be an admissible symplectic surface, and suppose it's nice. Then the supremum over all gamma and P of lambda, so that P of lambda is the set of all Reeb orbits of this fraction is greater than or equal to the area of the surface divided by the volume of the three-manifold. And what is this thing on the left-hand side? So well, the denominator, that's the action or the period of the Reeb orbit. And the numerator, that's the intersection number of gamma with sigma. So there are two cases. So the usual case is where gamma is not one of the Reeb orbits on the boundary of sigma. So then we're just literally counting the number of times that gamma intersects the interior of the surface. Each of these intersections algebraically counts as +1. So I add these up, I get some non-negative integer. Now, this gamma is also allowed to be one of the boundary Reeb orbits, and there the definition is more complicated. So there's a precise formula for it, which I'm not going to reproduce, but the idea of what the definition means is that if I start somewhere near the Reeb orbit, near this Reeb orbit gamma, and I follow the Reeb vector field so that I'm sort of going parallel or close to parallel to the Reeb orbit and staying in a neighborhood of it, and following this Reeb orbit around k times, where k is a large integer. So for any given k, I just have to sort of start close enough to gamma for that to work. So I take k large, I start close enough to gamma, I go around k times, I say how many times does that trajectory intersect the surface? And the number of intersections is approximately k times this gamma dot sigma. So that's the idea of what it means. And so then on the left side of the theorem, this intersection number divided by the period, you can think of it as the frequency of intersections. So it's like how many intersections do I have divided by the time that I spent going around the orbit. So this says that there have to be Reeb orbits with this lower bound on the frequency. Are there any questions about what that says? Right. Feel free to jump in and interrupt anytime if you have questions. All right. Now, the in this supremum here, it could be that we're only seeing Reeb orbits on the boundary of the surface, which is a little less interesting. In fact, it could be the case, and we'll see an example shortly, that there are no Reeb orbits at all intersecting the interior sigma. And so this is only talking about the boundary orbits. And if I want to see Reeb orbits that intersect the interior of the surface, then I need to add a hypothesis so that I'm not seeing the boundary Reeb orbits here. So I can do that here. So I have the same hypotheses as before, and I further assume that for every boundary Reeb orbit, the frequency is less than the area divided by the volume. So that means that, remember before, in the previous page, we said that the supremum is bigger than or equal to this. So if for the boundary Reeb orbits, it's all less than that, then there have to be some other non-boundary Reeb orbits to make that supremum what it is. And so then in this case, I get that the supremum of Reeb orbits, which are not boundary Reeb orbits of the frequency, is greater than or equal to the area of the volume. And in particular, if we don't even care about the frequency, this says that there have to exist Reeb orbits intersecting the interior of the surface. If they didn't exist, the supremum would be minus infinity. So this corollary is actually just an equivalent restatement of the previous theorem. Okay. So here's an example. So let's consider my favorite example, the irrational ellipsoid. So I take two positive real numbers, a and b, such that their ratio is irrational. And y is a three-dimensional ellipsoid where pi times the length of z1 squared divided by a plus pi times the length of z2 squared divided by b is equal to 1. This is a star-shaped hypersurface in R4. And like any star-shaped hypersurface, if you take the standard Liouville form and restrict it to the hypersurface, you get a contact form. And in this case, you can calculate the Reeb vector field, and it's given by this formula. So here theta 1 denotes the argument of z1, and theta 2 denotes the argument of z2. So the Reeb vector field it rotates the argument of Z1 at speed 2 pi over A, then rotates the argument of theta of Z2 at speed 2 pi over B. And then if there's a Reeb orbit where Z2 is equal to 0, and then this, I call it gamma 1, and this orbit has period A, because I go for time A, then theta 1 rotates around by 2 pi. And likewise, there's an orbit gamma 2, where Z1 is equal to 0, and it has period B. And because of my assumption that A over B is irrational, there are no other Reeb orbits, because if I start at a point where Z1 and Z2 are both non-zero, then these rotations are at an irrational ratio of speed, so you can never come back where you started. Okay. And now I'm going to make a admissible symplectic surface. So take any positive integers p and q that are relatively prime, and let's assume that b times q is bigger than a times p. If it's the other way, then it will just change some signs and everything else. I can make a cylinder. So you look at a subset of y where the absolute value z1, absolute value z2 are constant and non-zero. So that subset is a 2 torus. Because theta 1 and theta 2 can be anything. And in that 2 torus, I take a line of constant slope, which is in the homology class P, comma Q. So it's like a PQ torus knot in the 3-sphere. So I drew a picture here. So this is the toric picture. So y is, in the toric picture, y is just this line segment. And over each point in the interior of the line segment, I have a 2 torus. And the surface in that 2 torus is these diagonal lines. Okay. So now you can check that it's admissible, and its boundary is q times gamma 2 minus p times gamma 1. Now this intersection number, I didn't define it, and it's a little confusing, but just to give you the rough idea of what's going on here, like let's look at gamma 2 dot sigma. So if you start new gamma 2, well, the Reeb vector field is rotating theta 2 at speed 2 pi over, sorry. Well, as you go once around the Reeb orbit gamma 2, you're rotating around that Reeb orbit by a total angle of 2 times v over a. On the other hand, the surface, like the conormal vector to the surface, is also rotating, and the total rotation of that, the rotation number of the surface, is p over q. So you have to subtract, and then this is sort of the total relative rotation number of the Reeb vector field with respect to the surface. And then you'd think that that would be the number of intersections, except the surface has its boundary is a q-fold cover of gamma 2. So to get the correct number of intersections, you have to multiply by q. And the intersection number with gamma 1 is given by a similar formula. And then, so if you then divide this thing by the action of gamma 1 or this thing by the action of gamma 2, you get the same answer, which is BQ minus AP divided by AB. And in this example, the area of the surface by Stokes' theorem, if you look at this formula for the boundary of the surface, you get that the area is BQ minus AP, and you can also check that the volume of the ellipsoid is A times B. It's 2 times the volume of the 4-dimensional ellipsoid, which is the area of the triangle in the toric picture. So the 4-dimensional ellipsoid is has volume equal to the area of this triangle, which is AB over 2, and the three-dimensional ellipsoid has volume equal to AB. So that means that both gamma 1 and gamma 2 exactly realize the bound given in the theorem. So the theorem says that the premium is greater than or equal to this fraction, and for both gamma 1 and gamma 2, the left side is exactly equal to the right-hand side. And there are no Reeb orbits at all in the intersecting the interior of the surface. If I change the contact form a little bit to make one of these frequencies less than area over volume, then Reeb orbits in the interior of the surface would have to appear. In this case, it's kind of like a Poincare-Birkhoff theorem for area preserving maps from a cylinder to itself. Although the general case is much more complicated. Okay. Now, generically, my theorem is nothing new, because generically, K-Irier proves that the Reeb orbits are equidistributed. And one version of what he proved is the equidistributed means that there's a infinite sequence of Reeb orbits. These might be repeated, such that if you take any open set U and Y, you look at this fraction. So my notation here, the action of gamma 1 intersect U, that means how much time, as you go around the Reeb orbit gamma 1, how much time do you spend in the open set U? So I add up the how much time do these Reeb orbits spend in U divided by the total period of all of these Reeb orbits. And that will, in the limit as k goes to infinity, this will equal the volume of the open set U divided by the volume of the whole three manifold. So it says sort of like the average time that you spend in U is proportional to the volume of U. Now, if this equidistribution property holds, and if U is an admissible symplectic surface, well, then I can apply this to an open set U, which is obtained by taking sigma and flowing it by the rate flow for time epsilon. So this will be what I call a slab. So it's like a embedding of a small interval across the interior sigma into Y. And you apply that, you apply the theorem. Well, this action, the amount of time that gamma 1 spend inside U is epsilon times the intersection number of gamma 1 with the interior sigma. And the volume of U is epsilon times the area of sigma. So you take this fraction up here, you divide both sides by epsilon, and you get this equation here. This equation immediately implies that there have to be some Reeb orbits where the frequency is greater than or equal to the right-hand side. Otherwise, this fraction would be less than the right-hand side, and you get a contradiction. And here I didn't really need to assume that sigma is an admissible symplectic surface. I did assume that sigma is a symplectic surface. There's some results by Bechara Senior, Renievitz, and Salomo where they look at surfaces which are not even symplectic. They just assume that the total area is not equal to 0, but it could be negative. D lambda could be positive in parts of it and negative in other parts of it. So the upshot is that if equidistribution holds, which we know is true generically by Irier, then my theorem is sort of trivial. So the new part of my theorem is that I'm not assuming that the contact form is generic at all. Any questions so far? Okay. You all can hear me, right? Okay. I heard about some like during the COVID time, some professor like gave a 2-hour math lecture, and like all the screens of the students were blank because they were all like sick of this, and the sound wasn't working, but nobody told him. So he basically talked for 2 hours, and it's just like went into nowhere. So let me make sure that's not happening. All right, great. There's a quick application of the theorem to mean action and the Calabi invariant. So this is another way we can make examples of admissible symplectic surfaces. So let's take the unit disk. I'll take the symplectic form. I'll take the standard one and divide it by pi so that its area is 1. And let phi be an area-preserving diffeomorphism. And I'm also going to assume that near the boundary of the disk, phi is a rotation by some fixed amount, 2 pi theta 0. This will just make my life easier. And then there's a nice primitive, a beta of omega, 1 over 2 pi times r squared d theta. And then if I look at phi star beta minus beta, well, d of it is phi star omega minus omega, which is 0. So this phi star beta minus beta is a closed one form. On the 2 disk, every closed one form is exact. So it's d of some function f, which is defined up to adding a constant. And I choose that constant to make the restriction of f on the boundary equal to theta 0. And then the Calabi invariant of the pair phi comma theta 0 is defined to be the integral over d2 of f with respect to omega. So you could think of it as the average value of f on the disk. This is a homomorphism from the universal cover of the group of area preserving diffeomorphisms to the real numbers. Now, we can also look at periodic orbits with the map phi. And if I have such a periodic orbit, I define its mean action. So I denote this by action phi of gamma divided by its period. So this is the average value of f on the finitely many points in this periodic orbit. So the Calabi invariant is the average of f over the whole disk, and the mean action of a periodic orbit is the average value of f over the orbit. And then there's a theorem I proved 10 years ago, which says that if the Calabi invariant is less than theta 0, then the infimum of the mean action is less than or equal to the Calabi invariant. So roughly speaking, this says that the Calabi invariant, which is the average value of f on the whole surface, is to some extent seen by periodic orbits, because here we have the average value of f over periodic orbit. And the original proof for the theorem used a filtration on embedded contact homology induced by a transverse knot. And Oren Weiler, Joe Nelson, Aurora Pirna-Pasov, Barney Priam, and Rohil Prasad have various extensions of this theorem to other cases. And the theorem I just stated about the frequency of intersection gives a new proof of this result from 10 years ago, and it generalizes to any area-preserving diffeomorphism of a compact surface with boundary, as long as you assume a sort of flux condition. So basically, when I define this function f, I needed to know that this one form here is exact. So you have to assume some kind of exactness like that in order to even state a theorem. And if you can, then the analog of this statement holds. So let me show you how that works. So I'm just going to explain the disk case. So the dilemma to get started is that if I have a automorphism of the disk, and if I further assume that the function f is everywhere positive, then I can make a contact form on S3 with an open book decomposition where the page is a disk. the area of the disk is 1. The boundary Reeb orbit, its intersection number with the disk, in my sort of weird sense, is 1 over theta 0. And the return map from the disk to itself is sort of described in terms of phi. So if you start at some point x in the disk, then you will come back. It's an open book, so you have to come back to the disk. The time it takes is f of x, and the point that you return to is phi of x. So the picture looks like this. So here's the disk. I started at point x. I've followed the rate flow for time f of x, and I come back to the disk at the point phi of x. And in particular, if I have some periodic orbit of phi, then it's going to give me a periodic orbit of the ray vector field. And the total period of that Reeb orbit is the total time I have to travel around each of these intervals, which is the sum of f on the entire periodic orbit of phi. So you get that there's a bijection between the periodic orbits of the contact form, and well, you have the periodic orbits of phi together with one more Reeb orbit coming from the boundary of the disk. And if gamma is a periodic orbit of phi, then the number of intersections with sigma is its period d of gamma, and symplectic action is a phi of gamma. And furthermore, by assumption that phi is a constant rotation near the boundary of the disk, implies that this setup is nice in the technical sense that I defined earlier. So I can apply the theorem to it. And furthermore, the volume of this contact form is equal to the Calabi invariant. So basically, this is sort of the translation between area preserving maps of the disk and contact forms in S3. So if you believe all of that, then here's how we prove the theorem about mean action in the Calabi invariant. So first of all, to invoke the lemma, I need to assume that f is positive. And I don't know that a priori, but if you look at the statement of the theorem, I could just add some integer to theta 0. And if I add an integer to theta 0, it increases both the left and right-hand sides of this inequality by that same integer. And it increases f by that same integer. So without loss of generality, I can add some large positive integer to theta 0 to arrange that f is positive. Okay. Now, the hypothesis of the theorem was that the Calabi invariant is less than theta 0. And if you translate that using the dilemma, well, this says that the frequency of intersections of B, the boundary orbit with the disk, is less than the area divided by the volume. Because in this inequality, well, the action of B is equal to the area of the disk, which is 1, and B dot sigma, that's theta 0 inverse, the area of sigma is 1, and the volume is the Calabi invariant. So this inequality says that theta 0 inverse is less than 1 over the Calabi invariant, which is equivalent to the hypothesis. So then I can apply the corollary to get a Reeb orbit frequently intersecting the interior of the disk. So the frequency of intersection, the supremum of the frequency of intersections has to be greater than or equal to area over volume, which is 1 over Calabi. And then if I take the reciprocal of this statement, I get the infimum over periodic orbits of phi of the mean action is less than or equal to Calabi, and that's it. So the relation between mean action and Calabi invariant follows immediately from the theorem about frequent intersections. Any questions about that? Okay. So how am I going to prove this main theorem? So the technology that we use are what I call elementary spectral invariants. And these are a simplified version of the ECH spectral invariants coming from embedded contact homology. Um, it has similar properties, but a much easier definition. And what are they? Well, you input a contact 3 manifold, and you output a sequence of real numbers, a non-decreasing sequence of real numbers. And they have various properties. So there's a spectrality property, which says that each of these numbers is the total action of some finite set of Reeb orbits, depending on K. So these numbers are detecting periods or total periods of certain special finite sets of Reeb orbits. Second, we're going to have to talk about changing the contact form. So you can multiply the contact form by any positive function to get another contact form. And if you multiply lambda by e to the f, well, these numbers depend continuously on f with respect to the C0 norm on f. So f is smooth, but if it's the C0 norm of f is small, then ck of e to the f lambda will be close to ck of lambda. So the first two properties, they sort of follow kind of straightforwardly from the definition. And then there's one very non-trivial property, which is the Weil law, describing the asymptotics of these spectral invariants, which says that the limit as k goes to infinity of ck squared divided by k is 2 times the volume of the contact 3 manifold. And so in a joint paper with Dan Christopher Gardner and Vinicius Ramos, we proved a Weil law for the original ECH spectrum. And then there's a relation between the original ECH spectrum and these new spectral invariants. And you can use it to deduce this Weil law for the elementary invariants. In the case where Y is a 3-sphere, you can give a more elementary proof of the Weil law without using embedded contact homology at all. In particular, my new proof of the relation between beam action and the Calabi invariant for the disk does not use embedded contact homology or cyberwind theory at all. So it's sort of much lower tech than the older proof. Okay. Now, sorry, but we have to talk about yet more invariants here. So there are also some sort of 4-dimensional variants of 4-dimensional symplectic manifolds, which I call the alternative ECH capacities. And these are related to the spectral invariants of 3 manifolds as follows. So let's consider changing the contact form by multiplying it by e to the f, where f is a non-negative function. And then mf, this is a 4-dimensional region in the symplectization of y lambda, where you're in between sort of 0 cross y and the graph of f. So the picture looks like this. So this is the symplectization. The vertical direction is the r coordinate, which I denote by s. At s equals 0, you have a copy of y, and then there's the graph of f. And then in between y and the graph of f, there's this 4-dimensional open set mf. Okay. And then the last property of the spectral invariance that I need is that if you look at the spectral invariance of e to the f times lambda and compare them to the spectral invariance of lambda, well, they differ by this alternative ECH capacity of mf. So you have to put k plus L here, where k and L are some non-negative integers, and you have K here and L there. And these alternative ECH capacities, they satisfy another Weyl law, which says the limit of CL squared over L is 4 times the symplectic volume of this 4-dimensional region, which you can also write in terms of the difference between volumes between these two different contact forms. And you might ask me, all right, well, where are all these crazy invariants coming from? So let me briefly review the definition. The definition actually only takes a page. So this is for the alternative ECH capacities. This is the whole definition. So what is it? So let's suppose that X is a 4-dimensional compact Liouville domain. Then you take, it's sort of like a max min, although technically it's a supremum infimum. So you look at okay, X bar is a symplectic completion of X. So you take the boundary of X and you attach a half infinite line across the boundary of X. And J of X bar, these are almost complex structures which are compatible with the symplectic and contact structures. It's sort of a standard conditions on the almost complex structure, which I won't write down. Okay, so I lied. It doesn't quite all fit on this page because I omitted a couple of things. And then this moduli space MJ. So I look at holomorphic curves in X bar, which are required to go through K points in X, which are X1 through XK. And to avoid triviality, I don't allow any component of my holomorphic curve to be a constant map. Otherwise, I could easily go through all the points with just constant maps to each point. But the curve can be disconnected, and it has positive punctures asymptotic to Reeb orbits. And then this E of U is the energy, which is the sum over all punctures of the symplectic action of the corresponding Reeb orbit. So this number, well, it could be plus infinity. If it's plus infinity, then it sort of doesn't tell you much. But if this number happens to be finite, then it's a guarantee that certain holomorphic curves have to exist with an upper bound on their energy. For example, suppose I know this number is equal to 17. 17 is my favorite number. Well, that means that if I take any almost complex structure and I take any points at X, then I'm guaranteed to be able to find the holomorphic curve whose energy is at most 17 plus epsilon, or I can take epsilon to be as small as I want. So finiteness of this number is a guarantee of the existence of holomorphic curves with an upper bound of the energy. Here's a quick picture. So here's the lower part of the picture. This is the Liouville domain X. And I've attached this half cylinder to get X bar. I pick some points at X. And then there's a holomorphic curve going through these points, which is not really clear from the way I drew it, but this holomorphic curve is supposed to be going through these points. This asymptotic to some Reeb orbits, and the energy is a total action of these Reeb orbits. All right. And this was inspired by a construction of McDuff-Siegel for some similar things, which instead of looking like ECH, they look like rational symplectic field theory. Okay. But compared to the old ECH capacities, well, the old ECH capacities involve sort of like counting holomorphic curves determined by holomorphic curve by coordinate maps in ECH. And the new capacities, well, I'm not counting the holomorphic curves. I'm just sort of talking about whether they exist or not. And the definition might sort of look too simple to be usable, but surprisingly, it actually is. So you can compute it in examples and prove stuff using it. And then, so I told you what these capacities are for the Liouville domain. And then if I have some symplectic manifold, which is not a Liouville domain, like the MF that I was talking about before, that's the case I actually care about, then to define CK of that, I take the supremum of CK of any Liouville domain which symplectically embeds into M. That's a sort of a simple trick to extend the definition of the capacity to any symplectic four manifold. And then there's a variant of this definition, which I won't spell out, which gives you invariance of contact three manifolds. So given a contact three manifold, I look at half of the symplectization, the integral from minus infinity to 0 across y, and I make a similar definition where this half line cross y plays the role of the Liouville domain. So again, it's, CK is sort of talking about energy of the polymorphic curves that have to go through some points. Right. So if you accept that we have all the technology, I can now start a sketch of a proof of the main theorem. So the idea is I'm going to change the contact form and see what happens. And when I change the contact form, well, it's going to change the spectral invariance. It's also going to change what the Reeb orbits look like. But I'm going to change the contact form in a very controlled way. So what I do is so delta some positive number. I'm going to multiply the contact form by e to the f delta. And f delta is a bump function which is supported in a neighborhood of sigma, but it's chosen very carefully. So first of all, the volume gets increased. It gets increased by 2 delta times the area of sigma. This is not completely correct because I have to sort of cut off my bump function near the boundary of sigma. So it's actually slightly less than this, but I'm going to ignore that because this is just a sketch. And further, away from the boundary of sigma, the Reeb orbits stay the same, but basically, so there's a bijection between the old Reeb orbits and the new Reeb orbits, but the actions increase. So the action of a new Reeb orbit is the action of the old Reeb orbit plus delta times the number of intersections with sigma. So let me draw a picture to show you what's going on there. So this picture, so on the left side, so this is horizontally, this is sigma. Vertically, this is a small interval. So I'm modifying the contact form on sigma across this small interval. Now the old Reeb vector field just goes straight through sigma. I assumed that Reeb vector fields transverse to sigma, except for the boundary, of course. Now with my new contact form, there's some bump. I'm multiplying by some bump function supported on this interval across sigma. So the Reeb, if I follow the Reeb vector field, well, as I enter this region, now the bump function starts to increase, so it has some derivative. And if you calculate what the Reeb vector field is, the derivative of the bump function causes the Reeb flow to be deflected in the direction of sigma. So now I'm sort of somewhere else in sigma. But now I want to choose my bump function so that it's symmetric with respect to this interval from 0 to epsilon. So now as I'm getting ready to leave this region, the bump function goes back down to 0, and derivative of the bump function deflects the Reeb vector field in the opposite direction from before. And then I leave this region exactly the same place I left it previously. So this old Reeb trajectory goes straight through the surface. The new Reeb trajectory, it gets deflected inside the surface, but it comes out where it came out before, but now its action is bigger, sort of intuitively, because it, spent some time making some kind of detour inside of sigma. It wanted to like look around inside, sigma across an interval. So again, Reeb orbits gamma for the original concept for lambda away from the boundary of sigma are in bijection with Reeb orbits for the new contact form. And the action for the new contact form is the action of the old contact form, plus every time I intersect sigma, the action gets increased by delta. So delta is sort of how much time is spent on a detour in sigma. I'm going to ignore the Reeb orbits near the boundary of sigma because something more complicated is happening with those. And then the strategy for the proof is to say that suppose that there do not exist any Reeb orbits intersecting sigma with sufficiently high frequency. Well, then sort of these actions of Reeb orbits are not increasing very much. And you can argue that the spectral invariance of the new contact form minus the spectral invariance of the old contact form, that difference is small. And you can violate the capacity bound, because if you remember the capacity bound earlier, down here, this gives a lower bound on the difference between old and new contact forms in terms of the this region MF. Okay, so that is my strategy. That's the picture. I'm going to, like, the Reeb orbits near the boundary of sigma, I'm going to sweep that issue under the rug. Okay.
Is the bijection between the before the change and after is something you can do by hands, or is it clear like how to construct this bijection?
Yeah, so for the Reeb orbits, away from the boundary of sigma, this bijection is clear. It's constructed by hand. It basically follows from this picture. So if I had a Reeb orbit before, well, after I do the modification, you sort of have to write down the formula for the Reeb vector field, and then you see that the new trajectory sort of comes out exactly where it came out before. So if this point is sort of on a Reeb orbit, if I follow the Reeb flow starting the point, well, I'm going to cross the surface a number of times. Every time I cross the surface, I'm going to come out the same place as before. So I will eventually come back to this point. It's just going to take a little longer. That's what this equation says. Other questions about that?
Yeah, I just meant that like if you do these changes, you would expect that maybe some of them are not closed anymore, or maybe you could create new ones and stuff like this.
Yeah, well, for the orbits away from the boundary of sigma, it's a bijection. The only complicated thing is sort of near the boundary of sigma.
Oh, that's why you needed the niceness or something?
Exactly, yeah. So I need some control over what's going on there. What would be bad for me is if you had sort of, like before perturbing anything, if you have Reeb orbits near the boundary of sigma, it's like start near the boundary of sigma, and then they sort of wander away and go all around Y and go on a long odyssey, and then come back near the boundary of sigma, and I have no idea where they've been. Then that would mess everything up. But my niceness assumption assures me that before I do the perturbation, any Reeb orbit near, actually any Reeb trajectory near one of these boundary orbits stays near the boundary Reeb orbit forever. So I have a lot of control over what's going on with it. So I'm still going to like create a bunch of new Reeb orbits near the boundary, but you can check that they sort of don't mess up the argument.
I see, thanks.
Other questions about this? Okay. So then now we have to do a little calculation. So I'll just sort of show you basically what it looks like. So let's assume to get a contradiction, well, actually not to get a contradiction. Let's assume that there's some upper bound on the frequency of all Reeb orbits, which I'm going to call capital F. I want to show that this capital F cannot be too small. That's the goal. But let's assume that I have some upper bound on the frequencies. Now, as I'm changing the contact form lambda delta, well, for each delta, each spectral invariant is the total action of some finite set of Reeb orbits. Then you can look at the derivative of the spectral invariant with respect to delta. Now, if so I lied slightly. This sort of only works after some perturbation to make my lambda deltas generic. So it's a slight lie. Let's ignore that. So if you imagine that if this capacity is sort of carried by the same set of Reeb orbits, or spectral invariants, sorry, then as I change the contact form, the derivative of the action is well, I just have to, the derivative of the spectral invariant is I have to just look at the derivative of the action of that finite set of Reeb orbits. Now, but from this previous equation here, the action of a Reeb orbit is increasing. So the derivative of the action of a Reeb orbit is given by its number of intersections with sigma. So over here then, you get that the derivative of the spectral invariant is less than or equal to f times the spectral invariant. That follows from the line above. So then you can just integrate this differential inequality to get that ck for lambda delta is less than or equal to e to the f delta times ck for lambda. So let's just keep this in the back of our mind. To simplify notation, I'll let A denote the area of the surface. I'll let V denote the volume of the three manifold. And I'll let M denote this region M of F delta, which enters into the capacity bound. And now there are these integers K and L in the capacity bound, and you have to choose them carefully. So L is proportional to K by this equation. And then there's the Weyl law for CK, which tells you the limit of CK squared over K. And then it also just tells you by substitution the limit of CK plus L squared divided by K. And there's also a Weyl law for the alternative ECH capacities of M. And when you do a little algebra, you get this thing. So I'm just going let's ignore the details of this, and I'll just write it on the next page. So this limit is what you get from all of the Weyl laws that you know. On the other hand, by my argument about the derivative of the spectral invariance, I know that CK plus L for lambda delta is less than or equal to e to the f delta times CK plus L for lambda. And on the other hand, the capacity bound says that CK plus L for lambda delta is greater than or equal to CK of Y plus CL of M. And then if you plug this inequality into the previous limit, you get that e to the 2f delta is bigger than or equal to 1 plus 2 times a delta divided by v. And this forces f to have a lower bound. So if if f is too small, if f is less than a over v, well, I can take delta to be any positive number I want. So I just take delta to be very small, and then you'll get a contradiction to this inequality. So f cannot be less than a over v. So that means that if the frequency of every Reeb orbit is less than or equal to f, then f has to be at least a over v. And that exactly means that the supremum of the frequency is at least a over v, and that's what the theorem says. So that's QED for my sketch. And we have 1 minute left. Let me share a couple of open questions. So first of all, the theorem says, if you spell it out, it says that if I take any epsilon greater than 0, then there exists a Reeb orbit whose frequency of intersections is at least a over v minus epsilon. And then you could say, can I make this quantitative? So can I put some upper bound on what is the action of that periodic orbit in terms of epsilon? And the answer is yes. So you can use subleading asymptotics to do it. So when I tried it, I got some pretty bad upper bounds, like O of epsilon to the minus 1 over 30 or something crazy like that. Sorry, O of epsilon to the minus 30 is what I meant to say. So I got some very bad optimal bound. There's a new paper by Oliver Etmeyer, which recently appeared, which gives very good subleading asymptotics. So if you use that and maybe improve some of the arguments in the proof, then you can get a good bound on this. Second, I'd really like to remove the niceness hypothesis. I just wasn't smart enough. You could get some nice examples then. For example, if y is the unit cotangent bundle of a surface, then you can make some nice examples of admissible symplectic surfaces starting with geodesics. And this will tell you something about how many times geodesics have to intersect other geodesics, or how frequently. There's also the reverse inequality in the theorem. So instead of the supremum bigger than this, I have infimum less than that. This would follow immediately if you know equidistribution, but the question is, does it hold generically? I have no idea. You could look at all the frequencies and say, is the closure of that set an interval? I also have no idea. And finally, is there a generalization to higher dimensions? I suspect maybe not, but somebody needs to make a counterexample. All right, so thank you very much.
Thank you. Very interesting. Are there any questions?
So the niceness hypothesis, is it generic is it generic for elliptic curves or?
No, it's very non-generic.
Mhm.
I'm assuming because like an elliptic orbit says like the linearized return map is a rotation. But my niceness says not only is the linearization of the return map at the orbit a rotation, but actually the entire return map on some disk transverse to the Reeb orbit is a rotation. That's very non-generic. In general, you expect some complicated sort of KM picture with all these like weird variantorian stuff.
Mhm. Thank you.
So is there like some nice examples for such surfaces that you have in mind, like an interesting ones where the boundary is not the one that gives you the supermoon?
Um, so where the supremum is not coming from the boundary. Well, sure. So that's like the mean action and Calabi invariant thing is an example of that. So if we go back to that proof, um,
Right.
yeah, here, so like I had this hypothesis that the Calabi invariant is strictly less than the boundary rotation number. And that hypothesis is equivalent to saying that when I translate this to a contact form in S3, then the boundary Reeb orbit of the surface does not realize um, the lower bound on the supremum. So there have to be Reeb orbits intersecting the interior of the surface, which give rise to that lower bound. And those are exactly the periodic orbits of the map phi on the interior of the surface that I'm looking for in this theorem relating mean action to the Calabi invariant.
Mhm. And kind of maybe these examples, you can also construct a double cover on the boundary. Like.
Um, you want to you want to make cover of what?
Double cover on the boundary, right? You said that it's
Oh,
the
right. Yes. So yeah. So in this case, the surface is embedded, but in general, like um, the boundary of the surface could multiply cover some Reeb orbits. Um, so the example I made for the ellipsoid had that property.
oh
So here the boundary multiply covers gamma 2 with multiplicity q, gamma 1 multiplicity p. Of course, this example is otherwise uninteresting because the theorem only sees the boundary orbit. But if you perturb it a little bit, then the theorem will see orbits intersecting the interior.
I have a question, but maybe this is about Erie's paper. Like if you ran your proof using their hypothesis with this genericity, what was it, C infinity generic? Would your proof be like, would it be significantly easier? Or would it be the same? Like if you had some genericity to work with and use your proof?
Um, my proof, I'm not sure. Well, actually, my proof does use generosity in a way that I didn't tell you. So to make the proof work, I sort of first make some perturbation to make things generic, and I run the argument, um, and then I sort of then I have to argue that I can remove the genericity assumption or take the limit as that perturbation goes to zero, and so I have some sort of upper bound on the lengths of the ring orbits that I'm producing, which allows me to take a limit. So in the actual underbelly of the proof, there's some perturbation of things to be generic, which you then get rid of in the end. And then I'm not sure how this connects exactly to Urie's paper, although I guess you could say that everything I'm doing is some kind of refinement of Urie's argument. So that Urie's original argument for density involved proving a closing lemma for the ray vector field. And the argument was basically, let's change the contact form and see what happens. And so Urie argued that if you change the contact form, you have to create some ray orbits, because if you don't, then all the ECH spectral invariants stay the same, and this leads to a contradiction with the Weil law. So I'm doing sort of a more refined or fancier version of this, one where I'm changing the contact form and seeing what happens both to the ray orbits and to the spectral invariants, and trying to get some conclusion.
Okay, so if there's no further question, thanks, Michael, again.
Thank you.